All right, so we're going to look at another couple of tests on this video. So the first one, we have a series that looks like this, n plus 1 over 2n plus 3 raised to the n. And notice that kind of has the form, I mean, if we had a number in there rather than a function, that looks like a geometric series, right? And in fact, if you write out some of the terms here, right, it's not looking geometric, but you can see what would happen if n gets big. N plus 1 over 2n plus 3 is going to start to generate numbers like 101 over 203. That's really close to a half, right? And the bigger n gets, this fraction is going to start to become closer and closer to 1/2. So it's just like what we saw with the ratio test. This series is going to start to behave geometrically with an r value of 1/2. And so we have this test called the root test, okay, which means it would converge, right, if it has an r value of 1/2. So to get just to this part, so we can take that limit and show that it's 1/2, what we're going to do is to take the nth root of our sequence part of our series to the n. That's going to cancel it out and allow me to just work with the inside. And we know that limit will be 1/2, which is less than 1. And so, again, comparing it to a geometric series test, we would say that this converges. So the root test, very not too hard to use. Especially if you see things to the nth power, then the nth root of a sub n, if you get a limit r, and the interpretation is just like the ratio test, which is based off the geometric series test. If the absolute value of r is less than 1, it converges. Greater than 1 diverges. And just like the ratio test, if you do get 1, then there's no conclusion. The test fails. You'd have to use something else. Okay, so let's see an example of that. If I've got n plus 1 over 3 to the nth term, nth power, here you could probably use the nth term test, right? Clearly n's going to go really big, and then you raise it to a big power, you would not get 0. But the nth term test could also be used. If you take the nth root of n plus 1 over 3 to the n, you're just going to get n plus 1 over 3, which is going to give you infinity, which is bigger than 1. So we know our series would diverge by the root test. Here's one maybe not so obvious what's going to happen. I've got n to the 2n divided by 2 to the n squared. I mean, clearly both of those are going to get big really, really fast, right? So because I have things, both of them raised to some kind of an n power, I would take the nth root of my formula. Now remember, nth root really means it's like raising it to the 1 over n, right? This is the same thing as raising that to the 1 over n. So you would be left with just n squared on the top and n on the bottom. And if you take this limit, okay, I know you can do this. You can do a L'Hopital's rule a couple of times, or you know that exponential functions get bigger faster than power functions. This limit's going to be 0. And that would be our r value. And since that's less than 1, our series would converge by the root test. Okay. So the next test is a big one, okay? The alternating series convergence test. And so what this is talking about, there's a lot of series that are alternating, that have plus minus alternating between positive negative terms. So let's look at the alternating p series, or the alternating harmonic series, right? That's a special p series where p is 1. 1 minus a half plus a third minus a fourth plus a fifth minus a sixth. And one way to study this particular series is if we look at the sequence of partial sums, meaning, remember that this, we haven't talked about this in a little while, but you successively adding the first term, the first 2 terms, the first 3 terms, the first 4 terms, and you're getting fractions. And this could be modeled with a graph, and this graph gives us a lot of information, okay? So let's take a minute to see what we're doing. So I'm graphing n on the x-axis, and the partial sum is what I'm plotting. So s sub 1, when n is 1, my sum is just 1, so I've got a dot there at 1. S sub 2 is 1 minus a half, which is a half, so I've got to go down a half, right, to get to here. This distance is a half. And then to find s sub 3, I'm going to do 1 minus a half plus a third. So notice, to get to s sub 3 from here, I'm going to have to add 1/3, right? I'm going to have to go up 1/3, and that'll give me 5/6. To do s sub 4, I would have to subtract 1/4 from here, right? And what you'll see is each time I get a successive partial sum, I'm always adding or subtracting by a smaller amount. And so this sequence of dots you start to see is converging onto, think of it like a horizontal asymptote, which would be my limit, which would be my infinite sum. Okay, so that tells us a couple of things. Number one, it tells us that this thing must converge, right? These partial sums are converging onto a limit somewhere between 1/2 and 1. Okay, more about that on the next page here. But another thing I want to point out, since we have this picture here, this will be important as well, is that remember that we talk about the remainder or the error, right? R2 is the error in S sub 2. In using 1/2 as the sum, S sub 2 is 1/2. R sub 2 measures the error from 1/2 to the actual answer. So R sub 2 graphically would be the distance between S sub 2 and our horizontal asymptote, our limit. But notice that R sub 2 is less than, that distance is less than 1/3, which would have been the next term, right? That's what I would have had to add to get to S sub 3. Okay, so 1/3 is the next term, which is A sub 3, right? So what we have is R2 is less than A3. If you look at your graph, R3, in other words, this S sub 3, the error in S sub 3 is right here. Well, that's less than how far I have to go to get to S sub 4. So R3 is less than A sub 4. R4 is less than A sub 5 forever. So what is always true is your error, R sub n, is always going to be less than or equal to the absolute value of your next term. Remember, next term could also be written as A sub n plus 1. Okay, so that, we'll talk more about that formula coming up. But going back to this picture though, we can tell now, if I have any alternating series whose terms are getting successively smaller and approaching 0, the picture I just drew that we were talking about is going to look very, very similar, right? It'll probably converge to some different number, but those dots will eventually approach a horizontal asymptote. So this leads us to the alternating series convergence test. If I've got an alternating series, okay, now to be clear, the -1 to the n is what makes it alternate, and that could be to the n plus 1. As we've seen, I could have like a different thing, maybe a cosine of n pi, that any kind of a thing that makes it alternate, plus minus plus minus. It doesn't have to be -1 to the n. Now, 3 things have to happen. If, aside from the -1 to the n, if this formula here has to generate positive terms, so I don't want to mix any negative terms with something, right? That gets a little harder to study. This I know will go plus minus, so I don't want to have any minus terms here as well that might counteract a negative here or something. So as long as this is generating positive terms, the terms decrease. Another way of saying that is the next term is less than the previous term. And as long as the limit, as n goes to infinity, of just this part of A sub n equals 0, we can conclude that our series converges. Now, big warning here, this is a convergence test only. We can't use this alternating series test to prove a series diverges. If it doesn't meet one of these requirements, the best we can say is that the alternating series test cannot be used. We can't make the claim that it diverges, okay? Now, if one of these should happen to fail, one of these three requirements, it probably does diverge. So you'd probably have to use a different test though. Quite often it might be like an nth term test to prove it diverges. Okay, so here's a quick example. This is another alternating P series where P equals 1/2, right? That's 1 over the square root of n. So we know this part right here is only going to generate positive terms, so it satisfies the first part. Clearly, this is going to be decreasing as n gets bigger, and it's very simple to prove that the limit as n goes to infinity of 1 over root n equals 0. So by the alternating series test, the series has to converge. Alternating series, -1 to the n plus 1 of ln of n over n. So my a sub n is ln of n over n, which will give me positive terms, okay, definitely for n greater than or equal to 2, which is where I'm starting it. Now to show that it's decreasing, remember we can do that, we did this for the integral test as well, and so one way to do it is to take the derivative, right? And we can see that the derivative is going to equal 0 when n is e. And if you do a little sign chart with the derivative, we can show that the derivative must be negative for n greater than e, which means my sequence would be decreasing for n greater than e. As long as it's true for some positive number, then we're okay. And then finally, taking the limit of our sequence, we can show pretty easily that it's 0. Meets all three requirements, so it has to converge by the alternating series test. Okay, another example here. -1 to the n plus 1, 2n plus 3 divided by n plus 1. Now this one, if you check it out, you can see it graphically or taking the derivative. These terms will decrease for n bigger than 1. The terms do decrease. Maybe if you think about it graphically, it might be easier. If you were to graph this function, I think what you would see is the terms are going to get smaller. They do decrease. The trouble is that when we take the limit of that, it's equal to 2, which is not 0. So this, and you know that because this function would have a horizontal asymptote of y equals 2, right? And so the terms do decrease, but they don't decrease to 0. And so the alternating series test would not be applicable here, but that would be your cue to use the nth term test, right? The fact that that limit is not 0, and if I include the -1 to the n plus 1, that limit plainly does not exist, then the series has to diverge. Now I've got an alternating series involving n over n cubed plus 1. And so, okay, actually there's going to be a third. This will be our last test. We can obviously use the alternating series test, and I hope you'll agree this is only going to generate positive terms. The terms would be decreasing pretty obviously because you've got big powers in the denominator, and the limit would definitely be 0. So we can definitely use the alternating series test to prove it converges. But another test we could use is called the absolute convergence test, and here's what that says. Okay, if I were to take the absolute value of this whole series here, right? Now, remember this term has some positive and it has some negative terms, right? So what this is basically saying is if I took the negative terms, even the negative ones, and made them positive, if that converges, well, then it must mean the series definitely converges, right? In other words, let's write out some terms. So the first term is 1/2, and then minus 2 over 9, and then plus 3 over 28, minus 4 over 65, I believe. Okay, so what this is basically saying is Remember, if a sum diverges, it means the sum gets infinitely big, right? All of these negative terms have they bring the sum down, right? You're taking some positive numbers and then adding some negatives, you're bringing the sum back down. But what the absolute convergence test says is even if you make these negative terms positive and you still get a convergent series, well, then having them be negative, every other term be negative, gives it all the more reason to converge, right? Because you're making the sum smaller. So because the absolute value of this would just give me n over n cubed plus 1, and how would you know that converges? Well, that would be a fairly simple limit comparison test, right? This is behaving just like 1 over n squared. And you could do a limit comparison test with that and show that it converges. So therefore, this series also converges by the absolute convergence test. Okay, again, the idea is that if we make all the terms positive and the series converges, then the alternating series, which has negative terms, has all the more reason to converge. Now, another time to use the absolute convergence test would be like, say you have a series that has sine in it, sine of n over n squared. If you wrote out some of the terms, sine of 1 over 1 squared, sine of 2 over 2 squared, and so forth. Okay, this is in radians, by the way, right? Sine of 1 radian, 2 radians, 3 radians, those are all positive. So these first three terms are going to be positive. But 4 radians, remember pi is 3.14 radians. So by the time you get to 4 radians, you're actually down you're over here, right? 4 radians would be in the third quadrant. Sine is negative. Sine of 5 radians would be negative. So would the sine of 6. But then as you move around the circle, you're going to get positive terms, then some negative terms, then some positive terms. See, we wouldn't consider this an alternating series. An alternating series has to go either plus, minus, plus, minus, plus, minus, or minus, plus, minus, plus. You can't have a bunch of positives and then some negatives and then some positives. We don't consider that an alternating series. But because it does have some negative terms, if I use the absolute convergence test, if I took the absolute value of our series, well, clearly the absolute value of sine of any number is going to be less than or equal to 1 over n squared, which we know is a convergent p-series. So therefore, our series would have to converge by the absolute convergence test. Okay. One more bit about going back to the error. We talked about the error in the alternating series test when we were using that. So one question we could get asked then is, this was our opening example. We know this series converges. So if it converges, it has a sum. How many terms are required to estimate the sum of that series to within 1/1000th? Now remember, our alternating series remainder says the error in using the first n terms to approximate the series would always be less than or equal to the next term in the series. So r sub n will be less than or equal to, and we're familiar with this from the ratio test. We know to do a sub n plus 1, you just replace your n's with n plus 1. Now, -1 to the n plus 2 is either plus or minus 1. If we're inside the absolute value, we can just ignore it. So what we have is 1 over n plus 1 would have to be less than 1 over 1,000. If you flip both sides, change the sign, we can solve for n and figure out that we're going to need greater than 999 terms to get our sum accurate to within 1/1000th. Okay. Here's another one. This alternating series of 1 over ln of n, you can show by the alternating series test, it passes all of our requirements. I guess I'd have to start that at 2, though. Otherwise, that would be dividing by 0. So this series does converge. But let's say I wanted to answer the same question. How many terms would it be required so that to estimate the sum to within 1/1000th? R sub n is less than or equal to the absolute value of the very next term. That can be ignored. So we have 1 over ln of n plus 1 is less than 1 over 1,000. Flip, change the sign, exponentiate both sides, right, to get rid of the ln. And we get n is greater than e to the 1,000th power minus 1. Okay, you should try to just get a appreciation for how big that number is. It's a very, very, very large number. So what does that tell us? It takes, this series converges to a certain number, but it takes a long time before it gets even within 1/1000th of the actual limit. So it's a very slowly convergent series. Okay, on the next video, we're going to talk about what it means, what's the implication for a series to be absolutely convergent versus conditionally convergent.